Yeah.
Right. Hello to everybody. Thank you for being here with us. Today we will welcome Amy Ryan, who is an experimental volcanologist as a postdoctoral associate in the University of Minnesota. Thank you very much, Amy, for being here with us today and for having accepted to present some of your work, especially because it's a bit early right now in Minnesota.
A little bit.
So you're now working in the rock and mineral physics laboratory in the University of Minnesota, but you did your PhD in Vancouver in the University of British Columbia. And I think the topic that you're going to present today is related to this PhD work.
Yes.
And with us today, we also have Mike Hipp, who is a professor at the Earth Science Institute of the University of Strasbourg in France. And you also worked on the topic. So yeah, Amy, if you want to start your talk, the floor is yours.
Okay, thank you very much for that introduction, and thank you for having me. So as Tom said, what I'll be going through today is work that I did during my PhD at the University of British Columbia. And that work was on the the occurrence and timescales of solid state sintering in volcanic environments. And this work led me into material science literature, into mineral physics literature, but I'm a volcanologist. And so what I'll be presenting today is pretty volcanology heavy, but has tendrils that I think lead into areas of mutual interest with this group. So I'd like to emphasize now that while I'm talking about volcanoes at length, the processes I'm really discussing are about how fluid flow and deformational behavior change as unconsolidated granular materials begin to lose porosity and gain competence. So with that as a preamble, I'll give you a little bit of a crash course in volcanology. There we go. So all volcanic activity is driven by the exsolution and expansion of dissolved volatiles, namely water and CO2, but a few other gases come into play as well. And yet we see a diverse array of eruptive styles. This can include lava effusion, relatively quiescent lava effusion, beautiful fire fountaining, as we're seeing right now at Etna, and as we saw in Stromboli in 2007, as well as the explosive ejection of rock fragments, either to produce these big, beautiful plumes or ground-hugging density currents. And we can also get the extrusion of these spines of crystal-rich, dense magmas. So all of these processes are driven by the same driving force, which is the expansion of volatiles. But really the diversity of behaviors we see is an interaction between the magma viscosity and the ability of gases that are trapped or gases in the system to flow through the system. So if we take the example on the left of low viscosity magmas, gases there have an easy time expanding against the surrounding magma. They can flow through the magma relatively easily. And in this way, they bubble to the surface. You can actually see a bubble bursting event here that was captured at Kilauea in 1969. In contrast, in magmas that are higher viscosity, gases are trapped. So magmas become more viscous as a result of the chemical evolution of the melt component, but also because of the crystallization of solid phases. So in these crystal-bearing, a little bit more viscous magmas, gases are trapped. They have a difficult time expanding against the surrounding magma. They can't connect to other gas bubbles particularly easily, and they can't really leave the volcanic system. And so what this means is as a trapped volatile phase, they're sort of primed for energetic explosive events. What actually happens is trapped gases will exert a pressure on the surrounding magma that may strain it faster than it can relax. That disrupts the magma body and fragments the magma body. And that's when we get these beautiful explosive events. In some cases, the magma viscosity is even higher, and these are the types of systems that I'll be speaking about today. In these cases, the magma is actually solidified or nearly solidified in the subsurface, And so the landforms we see coming out of the tops of these volcanoes are crystal-rich plugs of magma, and we term these domes and spines. I'll be using those terms sort of interchangeably throughout this talk. They have slightly different meanings, but for the sake of this talk, just consider them sort of the same word. And it's important to consider these systems because they can be particularly dangerous. So I'd like you to think of them as essentially mechanically unstable corks in the top of a champagne bottle. And when that cork fails for whatever reason, either from the gases that are trapped in the subsurface or because it is itself prone to collapse and failure, we can have these mass casualty events, some of which are noted on the left-hand side, and terrifying scenes like this relatively famous video on the right. So it's really important to understand the dynamics that control dome and spine building eruptions. Observations of natural systems tell us already that there are different dynamics in play during these types of eruptions. So some domes or spines that extrude at the surface have smooth surfaces, which are quite unusual and definitely not what we would expect from natural systems. Thermal imaging and visible light images or photographs of these systems sometimes show that they have their own sort of internal structure, namely that there are these annular regions that can be high temperature regions and can be zones of localized outgassing. And we also see that dome and spine extrusion is related to brittle activity in the subsurface. We often see this type of repetitive low amplitude seismicity. This is a recording of seismic events during the 2004 to 2008 eruption of Mount St. Helens. And this is unusual compared to other types of seismic activity that we see during different eruptions. So if we put all of these observations together into some sort of cartoon about what's happening in the subsurface, it might look like this. There's a stiff column of magma that's working its way towards the surface. And because it's stiff, high shear stresses develop at the contact between that magma body and the surrounding rock. And those high shear stresses cause the rising magma to actually fracture, creating a zone of brittle deformation and a bunch of blocks of magma that are subsequently milled as that magma body is moving upwards. So ultimately what's created is a rock powder, and we call this fault gouge. And the continued brittle behavior plus gouge production ultimately creates an annular shear zone that surrounds the rising magma body. As an unconsolidated granular material, we can expect this fault gouge to have high intergranular porosity, which means it should also have high permeability, and it should be low competence. It's just a rock powder. So this should allow for efficient outgassing and relatively easy magma ascent as that magma body just moves upwards, sort of lubricated by all the powder on its edges. So what we see here, this is a picture of the 2004 to 2008 eruption of Mount St. Helens. This is one of the spines that was produced, and you can see here the smooth surface of the lava spine. And that's actually the exhumed shear zone. I'm going to be taking lots of sips of tea. I'm not used to talking very much living in isolation, so forgive me.
Amy, can I just ask a question quickly?
Yeah.
What does the word competence mean in this context? Is it about impact? Low competence, what is it?
Yeah, so I'm avoiding using the word strength because oftentimes I don't have a measurement of strength, but a material, I guess strength would be an equivalent term. So something that, is easily deformable. It's a granular material. It's a rock powder. I don't know if that's a satisfactory explanation.
Yeah, that's perfectly fine. Thank you.
Okay, thanks. So what we see is actually that the smooth surfaces are exhumed shear zones. Given what I've just told you about how shear zones form, you would expect that when you dug into one of these, you would find only gouge, only this rock powder. But when some colleagues of mine actually did this in 2010 on this shear zone here, what they found is not only gouge, but also a variety of rocks, including high porosity, weak or low competence rocks, higher competence than this, but lower than this, and low porosity strong rocks. So keep these pink and black rocks in particular in mind as we move forward. So when I started my PhD in 2016 in volcanology, we didn't actually have a mechanism we could invoke for the formation of these particular rocks. There was no existing hypothesis. So that was sort of my job in my PhD, is to answer the question, what mechanism is responsible for their formation? And it was my hypothesis that these rocks are the results of solid state sintering occurring within a volcanic system. I'm not sure how familiar you all are with solid state sintering, but it's essentially it causes unconsolidated crystalline particles to coalesce as a result of diffusion occurring at the contact points between adjacent particles, resulting in the formation of these crystalline necks and ultimately a loss in pore space, which is we could also call densification, and an increase in material competence, which I'll call lithification. High temperatures and pressures and small grain sizes accelerate sintering, and we know that solid state sintering does not require a melt or a fluid present to occur. Solid state sintering is very well studied in material science, but to this point, or in 2016, we were unsure whether or not it operated in volcanic environments on timescales relevant to eruptions. It was assumed that it probably could occur, but it was probably too slow to be relevant to actual eruptive activity, which is on a timescale of between months and decades in these particular dome building systems. So what I did to test this hypothesis is I conducted a series of hot pressing experiments wherein I took some of that volcanic fault gouge from Mount St. Helens, I put it into a sealed metal canister, and then I subjected it to high temperatures and pressures for a period of hours to days. Following these hot pressing events, the material was cooled and decompressed, and then I measured the final density, porosity, and permeability of the experimental products. And I used those physical properties as well as the experimental conditions to develop an empirical model that describes the relationship between experimental product density, pressure, temperature, and time. I have here a couple of images. Over here on the left is my starting material, again, a rock powder. And then I have 4 of my experimental products here. They're arranged both in terms of increasing temperature, pressure, and time, increasing experimental conditions. And you can see the actual range of experimental conditions up here on the right. But what you also see is that the experimental conditions are correlated with increasing density and material competence and decreasing porosity and permeability as we move from number 4 over here over to number 1. It's lost its label there. I'll be showing you quantitative density, porosity, and permeability data in a second, but to sort of speak to the question of what do I mean by competence, I want to describe for you something about the mechanical properties, I guess, of these materials. Unfortunately, I wasn't actually able to measure their strength because of the size and sort of preciousness of these samples. So all I've got are very qualitative data. For example, this is something, sample 4 here is something you can scratch with your fingernail. Number 3 here is something that you can scratch by dragging a screwdriver across the top. You can't really scratch either of these particularly easily. In order to break them, it requires a steel chisel and either a rubber mallet or a steel hammer. So what I saw is a really remarkable increase in material competence as a result of my hot pressing experiments. In terms of the microstructures that developed, this is what I tended to see. The coalescence of individual crystalline particles to adjacent crystalline particles by the formation of these necks of material. I've highlighted some of them with little yellow arrows, but they're abundant throughout this field of view. And as particles begin to coalesce, they create these patches where the intergranular pore space, shown in black here, becomes very reduced. In some cases, it's essentially eradicated because these patches are so well coalesced. For comparison, I have here an image from a different study. So I used a polyphase natural material. So, you know, there's some complexity in these materials that I was working on, But for comparison, this is sintered calcite produced using the same methodology, hot pressing experiments. And you see the same microstructures develop, these thin necks of crystalline material that are bridging the gaps between adjacent crystalline particles. A lot of my work to this point, has focused on how the physical and mechanical properties of my composites have changed. There's an ongoing area of work that I'm doing right now, which is related to what's happening sort of at an atomic level during these sintering events. I don't have very much data to share with you yet in that area of study, but I do have this. This is a series of energy dispersive X-ray spectra showing the distribution of different elements. And in a sintered material. And I've picked 3 elements of interest, aluminum, sodium, and potassium, because these are found in materials that make up about 60% of what I put into my canisters. They make up 60% of my starting material. Note that potassium and sodium are in a solid solution with one another, so we can expect them to be, they should be in the same sort of regions, maybe showing some local variability based on the history of the actual crystals that I put in, but they should more or less overlap. And they should always overlap with aluminum because they're all coupled together in the same minerals. But what you can see in these maps is that while aluminum and sodium show essentially the same distributions, potassium has done something or is distributed in a different way, and notably is concentrated in regions where sintering has caused particles to coalesce. So again, I say this is very sort of preliminary work on this side of the study, but what I'm seeing is that potassium is somehow playing a role in the sintering of these materials. Returning now to the physical and mechanical properties of my materials, I have a summary diagram here of relative density as a function of time and temperature and pressure, which are shown here in the legend. It's a little bit busy, but because it also includes 2 different experimental apparatuses that were used, as well as the addition of water. But what I'd like you to take away is that relative density increases systematically with temperature, pressure, and time. Also, slight changes in the experimental methodology don't really seem to affect the overall densification trends that I'm observing. I have here the measured connected porosity and permeability of my experimental products, as well as an estimated initial porosity and permeability of the starting material, the gouge. And what you can see is there's a reduction in connected porosity by up to 0.3 and a reduction in permeability by almost 2 orders of magnitude as a result of solid state sintering. You can see on here a curve. This curve actually isn't fit to the data. This is a universal permeability model written by Wadsworth et al. 2016. And overall, what I'm seeing is that my measured porosity and permeability data are well described by this permeability model. So as I get into the modeling portion of this talk, I think in the next slide, you'll see that I co-opt this Wadsworth model for a bit of my own work. So as I said, I developed an empirical model that describes the relationship between density and the experimental conditions, namely temperature, pressure, and time. You can see that empirical model here. There are 3 fit parameters that I solved for when fitting this model form to my experimental data. And what I can do with this model then is I can solve for relative density as a function of temperature, pressure, and time. I can then convert that relative density into a porosity, and then I can feed that porosity into the Wadsworth model and I can get out permeability. And what this allows me to do ultimately is to predict porosity and permeability loss as a function of temperature, pressure, and time. So I have here a little bit of the modeling that I've done. So I have a field showing a range of pressures. Note that pressure is increasing downwards, mimicking depth increase, and temperature. And I have marked on here a few different symbols indicating specific volcanic environments, including the shear zones that I was describing earlier. And what I can do with my model then is I can contour this for porosity and permeability loss respectively as a function of time. So I have here the expected porosity loss and permeability loss after 10 days in the top row and after 1 year in the bottom row. It's a little bit busy, so I've highlighted on here 2 specific contours in the porosity column. These are contours that mark a 50% reduction in porosity. And you'll note that materials that are above 700 degrees and above about 25 MPa in pressure are expected to lose nearly 50% of their porosity over a period of just 10 days. After a year, of course, this region expands, and we can expect materials that sit at lower temperatures and lower pressures to also lose a significant portion of their porosity. Likewise, I've shown on here where permeability has been reduced by 2 orders of magnitude, and you can see it's a relatively restricted range after only 10 days, but after about a year, there's a greater number of pressure temperature conditions where we can expect permeability to be significantly reduced. I'll remind you again that the timescales that we're concerned about in volcanic environments are those that range from months to decades. And so these are very significant results indicating that solid state sintering actually can cause significant porosity and permeability loss on the timescale relevant for many volcanic activities or volcanic processes. I'd like to switch gears here now and show you what else I can do with this model. But first I need to introduce a new volcano to you. So this is, this main image here is a picture of a lava dome. And this lava dome is a part of the Chaos Crags deposit that you can see in the inset here, which is located in Northern California in the Lassen Volcanic Complex. And all of these, this series of 6 lava domes erupted about 1,100 years ago. And then 300 years ago, a majority of Dome C collapsed. You can see the actual collapse deposit up here in the top of the image, giving us this beautiful exposure of the lava dome interior, as well as the shear zone that encircles the lava dome. As with Mount St. Helens, there's a little bit of gouge present, and you can see that most clearly here in this image, this silver region. But there are also the same sort of rocks appearing. So a high porosity rock and a low porosity rock. They are these buff and dark red colored rocks respectively. And again, these are products of solid state sintering. These are their measured connected porosities and permeabilities. So these are the high porosity rocks, the sort of sandy colored ones, and these are the dark red low porosity rocks. I have on here also the measured porosity and permeability of the lava that makes up the interior of the dome. And you'll note that some of these shear zone materials are actually less porous and less permeable than the material in the interior of the dome. I was also able, in this case, to actually measure strength. We don't have to talk about whether or not I can scratch it, which is great. So the measured uniaxial compressive strength of the dacite is about 50 MPa. The high porosity rocks tended to have a measured uniaxial compressive strength of about 20. There was one that we measured at 42. But the thing I'd really like to highlight is that the low porosity rock here is, has a measured UCS of 86 MPa. So it's 4 times as strong as the other materials in the shear zone and twice as strong as the material in the interior of the lava dome. I'll be returning to these thoughts about what these different material or mechanical properties or strength may mean in lava dome eruptions in a couple of minutes. But let's first get back to the model. So what I've done here is I've rewritten it in terms of porosity rather than relative density, and I've reorganized it to solve for time. And in this form, what I can do then is input some reasonable estimate of temperature, some reasonable estimate of a confining pressure, an initial porosity, and then I can solve for the time needed to produce a rock of some porosity I input here. So what I've done then is I've taken the average porosity of my high porosity rock here and my low porosity rock here, and I've solved for the minimum time needed to produce these rocks observed at the surface as a function of depth, which is a proxy for pressure. And those define these two sintering windows, shaded sintering windows here. So in order to produce the rocks observed at the surface, we have to have spent more time than is defined by this contour at the given depth temperature condition. Volcanic systems are dynamic, so we're not really talking about something static. Nothing's fixed in place for very long. The lava dome and the associated shear zone materials are always moving up. So what I wanted to do is see if I could use these sintering windows to actually recover the ascent rate of the lava dome when it erupted 1100 years ago. And so what I've plotted on here, in addition to these two windows, are linear ascent rates. They appear nonlinear because of the log scale of the x-axis. And I'm looking for the ascent rates that pass through both sintering windows. What I found then is that the Dome C lava must have been moving up at less than 10 meters per day or less than that in order to produce the actual units observed at the surface. If the lava dome was moving up any faster than that, it wouldn't have remained in the subsurface long enough to produce the rocks that we see at the surface, particularly this low porosity one here. To show you that that estimate of 10 meters per day isn't unreasonable for a dome building system, for comparison, the Mount St. Helens eruption was characterized by linear ascent rates of less than or equal to 10 meters per day. And the Mount Unsen eruption, the one with that fantastic video from earlier in the talk, had an observed linear ascent rate that was a little bit faster, between 13 and 40 meters per day. But ultimately, what I've done here is I've used this model, which is calibrated on experimental data, to recover volcanic ascent rates. This makes it a volcanic geospeedometer. I'm getting into the last portion of my talk now. So what I want to do moving forward is consider how the effects of solid state sintering sort of compound one another. So I've observed that solid state sintering causes porosity loss, permeability loss, and material strengthening. I want to think about how those three changes feed back on one another in relation to explosive activity in these dome building systems. But if I were to write my sort of thoughts about that a little bit more generally, I think as you all think about fluid flow and porous materials, I think you'll recognize these statements as familiar perhaps to your own work. So again, I'm going to be talking about volcanoes, but I think what I'm discussing is more broadly relevant, even outside of geology. So I'll remind you that even slight losses in permeability have the potential to suppress fluid flow. And as a consequence of that, if there's a constant supply of fluid, you can imagine that there's a back pressure that builds behind a sintering body. Material strengthening is also going to make materials that are more resistant to deformation. So ultimately what we come to is that there will be some competition between fluid pressurization and material strengthening that will ultimately dictate how fluid can actually flow through the system and the observed in volcanic context outgassing patterns. So I'm going to return to my cartoon here. So this is our initial condition. There's a shear zone filled with gouge. And that gouge is an unconsolidated material that initially allows for efficient outgassing and magma ascent. So this is just after the shear zone is formed. My experimental work, though, has showed that the gouge won't remain unconsolidated for very long, and it will begin to sinter. And as a result of sintering, we'll produce a high porosity rock. There's some examples from nature and from my experiments up here. As a result of that sintering, there's a loss of porosity and permeability and an increase in material strength. So what you can imagine then is the outgassing in this volcanic system becomes suppressed, and the shear zone transitions from being a rock or a powder to a sort of jacketing solid material. And you can imagine it's more difficult then for the magma body to move upwards as it's sort of pinned in place by this solid outer layer. Continued sintering, of course, will produce an even lower porosity rock, which will cause even more significant permeability loss and significant strengthening. So there may be conditions then that outgassing and magma ascent actually cease. And you can imagine then that gas pressures, which I've been sneakily showing here as a red region, will begin to build. If those gas pressures become sufficiently high to exceed the tensile strength of the shear zone materials, the shear zone can reasonably fracture, causing an explosive ejection of trapped gases, as well as an ejection of particulate. Now, with the disruption of that shear zone, you can imagine it's a bunch of jumbled blocks now that will be milled by the upwards motion of that newly freed magma body. And what we return to then is our initial condition, albeit this time the gouge that fills the shear zone is a second generation gouge. So this is my sort of conceptual model for how all of these changes as a result of solid state sintering might fit together. But what I actually see in nature is evidence for this. So if we return to chaos crags and we look at some of the shear zone materials, here are some of the microstructures that I observed. These are two images. On the left, it's an optical microscopy image, and on the right, it's a backscatter image of rounded clasts of a low porosity, strong rock fragment within a high porosity, sort of weaker one. Now, in order to get these particular textures to form, the following series of events must have occurred. There must have been a gouge. It underwent sintering to first become a high porosity rock and then a low porosity rock. In order to make clasts, that low porosity rock must have been disrupted and fractured. In order to produce rounded clasts, there must have been some sort of milling. And so we can imagine that there's another second generation gouge. That gouge underwent sintering, and that's how we can produce the material seen in the previous image. If I overlay my cartoons on here, what we're seeing from these natural materials is evidence that solid state sintering not only can, but has caused cyclical explosive activity in this particular dome and spine building system. And I think this extends to other dome and spine building systems around the world. I'm going to conclude now, not about volcanology so much, but as sort of general statements about how fluid flow and deformation change as a result of these changes in unconsolidated granular material. So the effects of solid state sintering, or any sintering process really, this could be liquid phase sintering, liquid assisted sintering, will be the loss of pore space, a loss of permeability, and an increase in material strength or material competence. And these property changes will be directly dictated by the rate of sintering. So ultimately, if we want to be able to predict fluid transmission or deformation rates, we really must understand sintering rates at a range of relevant conditions. For me, those are volcanic conditions, but you can imagine this could be sort of any pressure, temperature, time, space. So with that, I'd like to thank you for your attention and ask if there are any questions.
Right, thank you very much, Amy, for your presentation.
Thank you.
I'd like to invite anybody here to ask questions, and you can do this either vocally by turning on your mic, or you can also use your chat window, and then we can read your questions.
I have a question. Thanks for the nice talk, Amy. So I'm wondering about the presence of fluids. Mm-hmm. So I would imagine, well, maybe you can tell me if there's many fluids in the subsurface around volcanoes. And if, like I recall you had this plot of densification with time where all the water saturated mm-hmm. samples didn't seem to densify.
Yeah.
And I guess based on that question, if it's possible that pressure solution creep could also be operating as well as solid state sintering.
Yeah. Yeah, so in volcanic environments, we can expect fluids to be present often. Sometimes that fluid is melt, and then the process or the macroscopic process is the same, but you could describe it as like a liquid phase sintering or liquid assisted sintering. If there are other fluids present, other liquids present or other gases present, yes, there's the potential for either precipitation of phases, which can lead to densification, or as you say, as pressure solution. But I think the environments in which you would find that, for example, my shear zones, you don't see fluids present enough to support those densification styles. But if you were to imagine a crack in the subsurface, maybe through hydrothermal systems, which are associated with volcanic environments, yes, then the dynamics of densification would change, and the mechanism is probably closer to what you're describing of pressure solution or some other mechanism.
Thanks.
Yeah.
So, Amy, is there a competition between the formation of the gouge itself, which I guess depend on the shear velocity of the dome, and the actual healing, which is the sintering? Because I think on your last slide you just described something which is a bit sequential. So you have phases of healing and phases of producing the gouge. But yeah, presumably this could be a all synchronized process. Yeah,
obviously my cartoons are simplified, as you can imagine, as all cartoons are. But yeah, obviously the time it takes to make some of these shear zones are extensive. So the time scale of making that larger shear zone body exceeds that of the healing time scale associated with solid state sintering. So of course, I think the distribution of these well-sintered materials will be heterogeneous. It wouldn't just be the whole thing blanket becomes low porosity or high porosity material. And we do sort of see this in investigations of natural shear zones. So there's definitely a competition between them. I can't necessarily say right now how that would play out, but you're right to identify the competition.
Thanks.
I have a quick question. So yeah, the permeability measurements that you've shown, these are gas permeability, right?
Yes.
Do you ever have any scenario where you have actually like fluid flowing through the porous structure after the sintering? Or is it always gas?
We tend to think about gas. This might be, Mike, if you're up for it, I might kick this one to you because you tend to work on a variety of different porous materials. And I know in his group, he studied, for example, liquids flowing through volcanic materials.
You're trying to see whether I'm watching.
Yeah, exactly. Are you present?
Good test.
Let's see if I can pass the test. So yeah, with volcanic systems, it's a bit of a mixture. In the edifice, we have I think it's safe to assume that volcanoes are also giant aquifers of meteoric water, but also of really nasty hydrothermal fluids at depth. And so those are like sloshing around. As magma moves up through the conduit or up through dikes, it decompresses and loses its volatiles. And so there's like water vapor, CO2, all sorts of other gases, nasty ones coming off the magma. And then what you can see as a bystander, an observer, is you can see and also measure gases that are billowing from the top of the volcano. And so I think that's what's nice about volcanology. Everything is relevant, and you can find a scenario for basically most things. I'm not sure that the water permeability would be greatly different in these rocks because there isn't so much in terms of clays, but it could be more important as things become more altered. And so in volcanology, there is a lot of gas permeability measurements, as less so in terms of water. I think both are relevant. And because volcanic rocks basically alter to clay, if given enough time, they're basically sitting in a horrible cauldron of hydrothermal fluids. Then water permeabilities might become more important because of swelling clays and such like. Okay, well, hopefully that answered some of it. I can
Thank you,
go
Mike.
back.
Do we have some extra questions?
Hello, Amy.
Hi, nice to see you again.
Thanks for the talk. So I'm just wondering about sintering and whether so at the temperature you mentioned, I wonder whether you could also have viscous sintering at the same time, and what difference it would make in terms of process.
Yeah. In these materials, there is no glass present, and we're below the solidus where you would expect melt to, or the materials to begin to melt.
Mm-hmm.
So I'm confident in saying the materials that I've looked at here are not experiencing any sort of viscous sintering. But were melt to be present, you can imagine, as you know, because you work on this, the time scale of sintering will be so much faster. Maybe not to the point of pure melt, where you're talking about seconds in some cases, but there will be definitely an acceleration of the densification, an acceleration of the loss of permeability, and you'll see the same sort of material strengthening pattern. Maybe the strength that you reach is not exactly the same, but you would see the same sort of trends.
Okay, yeah, sure.
So my process is really the slowest one, and it's still like relatively fast, which is good news.
I have an extra quick question, if you will. You mentioned at the very beginning of the talk that at the surface you have some, let's say, unexpected flat morphologies in the structures at the top of the volcano. When I mean flat, I mean non-ruggous. I might have missed it, but is it related to the shearing, or is it since regulated? Or?
You mean those smooth surfaces?
Yes.
Yeah. So the smooth surfaces are actually the shear zone that's been carried up along the side of the lava dome. Sorry. So they're not actually the dome that's been sheared off. It's the shear zone on the edge. I don't know if I'm describing that well, but that's why in some cases with spines, you see that beautiful smooth surface is because it's brought the shear zone along with it onto the surface.
So it is sintered, basically.
Yes, it is. It is sintered often. Maybe the outer layer will be the gouge material. Some of the observations from Mount St. Helens in 2004 to 2008 was really, really well monitored. You could actually see the powdery gouge sort of like flowing down the side of that steep edifice. So that's how people initially estimated that this was the shear zone, that this is a powder layer. It was only through later exploration into the actual dome that they could say, or the crater, you could actually see the sintered material, and that's where my work picked up.
So as a question back to the core lab team, is there instances where solid state sintering is of interest to, because Amy gave a volcano flavor to it, and but mentioned that quite rightly that it's useful across the board, and so we discussed over the last years about the transversal interest of this type of mechanism, but do any of you see like something like directly applicable to this type of process?
Well, I've been, and I think not only me and other people in the lab have been I've been studying fractures in sintered material. So what we do is we put usually PMMA plates together, and we put them in the oven under pressure. And then we have only one body with a weak plane in between the plates, and then we can fracture them and see, study, for instance, the fracture dynamics. So in these projects, we don't really care much about, I guess, the actual porosity or permeability, but we definitely wonder about the strengths that you get from the sintering. And because we use this object as experimental bodies to be fractured, usually we would like them to be quite consistent. And from experience, it's actually more complicated than that. It's, you can do the same cooking recipe and have two different strengths at the end. So it's a bit of a difficult experimental material. So in this context, some of us have used definitely solid sintering. I'm not sure if other people have used it in more pore flow related topic.
But you're more interested in how it breaks rather than how it forms, I guess.
Yes, definitely. But knowing the strength based on initial conditions and the PT condition that you apply, and of course the time that you apply these conditions, that could be interesting because we break it and then we can kind of measure the strength, but we never know exactly what we're going to have until we try.
Well, volcanoes are full of granular material that's been more or less jumbled back together by a variety of processes, including the one that Amy was talking about. So fractures through those sorts of materials is of interest, definitely, to those of us with a volcano interest, let's say.
Mm-hmm.
I'm not sure, maybe someone who is a bit older in Pola than I am can let us know if there are other sintering related topics that usually come out.
I couldn't think of any directly connected to the experiments that I've been doing. I do experiments at Pore Lab, but I'm sure that the topic is of overall importance to porous media physics. I don't know if it happens. It probably does happen in natural systems, like in natural aquifers and so on. And as you've shown, like for instance, in an aquifer, you have the pressure, you have the time. I don't know if you have the high temperatures that you typically have in a volcano, but you have the mechanism to have sintering. I don't know if it does happen, but it probably does. And it does change permeability and other things. So it changes the way you could exploit the aquifer, take the water out. So for sure, it's very relevant for the field.
I think also for fracture healing, this is important, like the problem you are working on, Tom, for instance, where you also can, create the bonds that is depends on temperature, and it's a kind of a part of the same problem in a way. I think also, like Francois has worked on fracture healing in Jord.
For sure, I think that this type of thing is just as applicable for fracture healing, as you said, at fault zones. So Amy was speaking mainly about these quite specific faults that are surrounding these lava domes and lava spines in volcanoes. But if you've got a crustal scale fault through some sort of granite, it creates gouge, and that gouge is coming back together through like precipitation and mineralization of hydrothermal fluids, but also of these sorts of mechanisms. I think that the point that Amy pointed out a few times is that I think this mechanism has been largely dismissed because people assumed that, especially volcanologists assumed that that it wasn't happening fast enough for it to be interesting, and so it was kind of brushed under the carpet at least in the volcano sense. But like a lot of things, material science is several decades ahead of where we are.
Absolutely, yeah. Yeah, I think to sort of build on that, I think we really, with respect to solid state sintering, we really don't know. I found evidence for it in a particular scenario or a particular setting, but we really don't know where the cutoff is, where it becomes irrelevant and where it gets taken over by, for example, as Mike said, precipitation of new phases or pressure solution, or some of these other different densification mechanisms, which will kick on depending on fluid presence or the particular chemistry of a fluid, etc. So it really hasn't been explored how relevant it is sort of across scales, but you can imagine it's a continuum of behaviors. And so it's good to begin to consider this at least as, again, sort of the slowest mechanism and explore timescales from there and yeah, carry forward.
All right. Well, thank you very much again for having joined us today. And
yeah, thank you for having me.
If there are no other questions, I guess we can call it a day.
Great. Thank you.
Thank you very much.